All right, today we're talking about how to write the equation of a polynomial, like a quadratic, a linear function, a cubic function. We haven't even talked about some of these yet. Cubic functions that look like that. Quartic functions that look like that. All kinds of cool looking graphs based on points that we're given. And to do that, to come up with the equations of these, we're going to need some consecutive points. So points that are right next to each other. And you can see we were given some tables here. We've got x, we've got y, we've got these 1, 2, 3, 4, 5, 6 consecutive points, which is good. Sometimes we might need more or less than that to come up with it, but 6 is usually a pretty good number here. So use finite differences to determine the degree of the polynomial function that will fit our data. Okay, so what a finite difference is. So remember that the word difference in math means subtraction, right? Answer to a subtraction problem. So what we're going to do is we're going to take the output values, the y's, and we're going to find the difference between our consecutive points. To do that, we're going to subtract kind of from the right to the left. So we're going to subtract 39 minus 15 is 24. 15 minus 5 is 10. 5 minus 3 is 2. 3 minus 3 is 0. And 3 minus, be careful on this one, negative 1. Minus a negative becomes plus a positive, and we end up with positive 4. 3 minus negative 1 is positive 4. Okay, and this is something called the first order difference. And what we're looking for when we're doing this is I want to know, did I get a constant back, like the same value every time I subtracted? And clearly we did not. And what that tells me is this did not come from a first degree polynomial. So this did not come from an equation of a line. All right, so my data does not represent a line. Okay, that's fine. What we're going to do is repeat this with our new values. So again, subtracting right to left. 24 minus 10 is 14. 10 minus 2 is 8. 2 minus 0 is 2. And 0 minus 4 is negative 4. Okay, these are our second order differences. And again, we're looking for a constant here. And we did not get a constant. We have 4 different values again. So what that tells me is this did not come from a second degree polynomial. It did not come from a quadratic. So this is not a quadratic function. It must be something of a higher degree. So we're going to do this again. 14 minus 8 is 6. 8 minus 2 is 6. And 2 minus negative 4. Remember, minus a negative becomes plus a positive. And we get 6. 6, 6, and 6, the mark of the beast. We've got a third order difference. Is constant. And that tells us that this comes from a third degree polynomial. So things we've been talking about before, like quadratics and lines, are forms of polynomials. We're going to talk about higher degree polynomials more in next chapter. But this would be something where we have like x cubed, some term with x cubed. We'll call it ax cubed, and bx squared, and cx to the first, and then d, right? And then maybe y is equal to this thing. So this comes from some sort of cubic polynomial. And in fact, in a little bit, we'll talk about how we can find the equation. And we can even graph it and show that all of these points are on that graph, which is pretty cool. So that's what we're going to be doing. But let's try one more of these. Okay, so number 2, if you want, pause the video, try it out, see if you can figure out what degree polynomial this comes from. All right, how'd you do? If you did this one correctly, you should have come up with a second degree polynomial. So if you subtracted our numbers correctly, and you can check your numbers with mine here, you should have come up with negative 4 for everything the second time we did this, which means the second order difference is constant, so it comes from a second degree polynomial. And in this case, that's a quadratic. That's what we did in the previous chapter, right? It's all on quadratics. And in fact, we can find the equation of this quadratic, which we're going to do in our next slides. Okay, so now we have a few more examples here. It's asking us to use finite differences and a system of equations to find the polynomial that fits our data. And we're going to use technology to help us solve these systems. So it's a good thing we just learned how to do that. Okay, so again, we've got these 6 consecutive points. We're going to use our finite differences. So let's do that first. All right, here are our finite differences. My first order difference was not constant, but my second order difference was. So we now know this comes from a quadratic, or a second degree polynomial. Okay, so what we're going to do is we're going to start with x squared as our highest degree. And to write kind of our generic polynomial here, we're going to put an a in front of it as our leading coefficient. We're going to need something in front of x to the first power, which we'll just throw in the variable b. And we need all the way to the constant, which we're just going to call c. And so we've seen this before. This is the standard form for a quadratic, so it shouldn't be unfamiliar. But to write the equation of this quadratic, remember in our equations that y and x will always be there, but we need to figure out the 3 values of a, b, and c, which means we have 3 unknowns. And guess what? To come up with 3 unknowns, we need 3 equations. Oh my gosh, it's like we need a system of equations. It's all coming together. Well, how do I get 3 equations? And the answer lies up here. They've actually given me 6 pieces of information where I could write 6 equations if I needed to. And so here's how we're going to do this. 1, we're going to flip this y to the other side. We're going to put equals y over here instead. Okay, I know that looks weird, but because I'm going to want to use matrices to solve my system, remember when we used matrices, that constant it was equal to was always over on the right? That's why we're setting this up this way. Okay, so here's what we're going to do. We're going to plug in some points. So let's plug in, and we'll just start with some nice easy values. We're going to plug in 1 for x. Remember, these are our y values, and -4 for y. So let's do that. We're going to plug in -4 for y. So that goes over here on the right. And everywhere we see x, remember we're substituting in for x here, so I'm going to have x squared plus b times x plus c. And we're plugging in our x value of 1 and our y over there of -4. Okay. Down towards the bottom here, I'm going to simplify that equation. I'm going to leave some space for my other equations. But down here, we're going to have 1 squared is 1a. I'll even just leave the 1 in front of it. B times 1 is 1b. And this is really just to help remind me when I put it in is the matrix that there's a 1 there. We have 1c equals -4. Okay, so this is our simplified version of the equation. We're just writing it down here. Okay, well, we need to do this 2 more times. So let's go to our next, probably easiest point, the next smallest value of x to plug in, of 2. So we're going to plug in 2 everywhere we had x. And for y, we're plugging in 0, the y coordinate of our point. Okay, well, 2 squared makes 4. So we get 4a. 2 times b gives me 2b. We still have our 1c, but this time it equals 0. There's my second equation. And let's use probably the next easiest x to plug in of 3. So 3 squared plus b times 3 plus c equals 0. Okay, well 3 squared is 9 times a, so 9a. Then we have 3 times b, which is 3b, our 1c, and this time, whoops, equals 10, right? Not 0. Apologies. It's 10 is our y coordinate. Hopefully some of you were probably screaming at the screen right now telling me I made that mistake. All right, here is what I can essentially put in as my matrix, right? My coefficient matrix. 1, 4, 9, 1, 2, 3, 1, 1, 1, -4, 0, 10. And we're going to use technology to help us solve this. All right, so here we are in our matrix website again. We need a 3x4, 3 rows, 1, 2, 3, 4 columns for this system. So we're going to tell it to set matrix. We're going to put in our coefficients 1, 1, 1, negative 4, 4, 2, 1, 0, and 9, 3, 1, 10. Again, tell it to do with the detailed solution here, but it's found my values. Go ahead and show solutions. We're looking at that matrix. Good, we got all ones in our main diagonal. We've got zeros everywhere else in that 3x3, so there is one exact solution. And it looks like our A value, remember in this case, this is an A, B, and C column. So A, 1A is 3, B is negative 5, and C is negative 2. 3, negative 5, 2. All right, we're not quite done. We still haven't written the equation of this. So now, if I come back up here and we plug in our values of A, B, and C, we're going to get y equals 3, there's my A value, x squared, minus, because B is negative 5, minus bx, sorry, minus 5x, and then plus c. And since c is negative 2, it's minus 2. Okay, well, how can I be sure if this is the correct equation? Let's graph it. All right, here we are on Desmos. I've typed in my equation, 3x squared minus 5x minus 2. Let's convert it to a table. You can do that by clicking the cog here. Click Convert to Table. Now, it only gives me specific values, and from what I have on my table, it doesn't go too high up. It only has 1 and 2 on there, but we can add more in by just typing them in. But notice 1 is at negative 4. That matches. 2, 0. Let's try 3, should give us back 10. Nice. 4 gives us 26. 5 is 48. 6 is 76. We did it. We found the quadratic that goes through all of those points. Pretty awesome. Okay, an alternative way of solving your system, there's another website here. I believe this is called, CowPy. You can do different systems here. So you could have also typed in, instead of x, y, and z for a, b, and c, you can just type in your coefficients like you did with our matrix. And if you type all these in, it will also give you back our values, but it's going to show them, of course, as x, y, and z. So I hit solve, and there we go, 3, negative 5, negative 2. So a different website. I'll link this one. Maybe you like this version better. They're roughly the same, and you can see up here it's got different size matrices or systems to solve. All right, let's try number 4, see what we get. Let's start by doing the finite differences. All right, here are my finite differences. I ended up getting 6 again, the mark of the beast. I don't know why these are all 6s, guys. It's just coincidental. But we get a 3rd degree polynomial. We had to go to our 3rd order differences here, which means x cubed is the highest degree. So we'll need a variable in front of that, like a. We'll need something in front of x squared, like b. We'll need a variable in front of x to the first, like c. And then we need a variable for our constant, d. So we could put y equals in the front, but like we talked about here, because I'm going to want to set it up like this system, I'm just going to go ahead and throw that y over at the right. Okay, but that does give us 1, 2, 3, 4 unknowns to solve for, a, b, c, and d. And if you've got 4 unknowns, guess what you need? 4 equations. So just like we did before, we're going to plug in an x and a y and create 4 equations. Remember, we've got enough technically to make 6 equations if we needed to. So that's okay. It's not too bad. We just have to cube our x value here. So it's a times x cubed plus b times x squared plus c times x plus d is equal to y. So let's plug in our values. Let's start here. 1 for x and negative 4 for y. And so my new equation, when we simplify this, 1 cubed, of course, is 1. So we get 1a. 1 squared is 1, so we get 1b. Then we have 1c. We do have 1d, even though we didn't write the 1 in front of it beforehand, equals negative 4. There's my first of 4 equations we need. Okay, so let's plug in our next points here. Just setting it up with our blanks for x, c times x plus d. All right. Next up, we're going to plug in 2, negative 6. So 2 for x, negative 6 for y. So 2 for x, negative 6 for y. All right, so down here, 2 cubed. Ooh, be careful here. 2 times 2 is 4, times 2 is 8. It becomes 8a. Then we have 2 cubed, which is 4b. Sorry, 2 squared times b. 2 times c makes 2c. And then we have our 1d again equals negative 6. There's our second of our 4 equations. Okay, so we're going to do the same thing. Plug in our next 2 values. So let's plug in 3, negative 2 next. Okay, so here's all my values plugged in. 3 for x, negative 2 for y. 3 cubed, 3 times 3 is 9, times 3 again is 27a. 3 squared makes 9b. 3 times c is 3c. Once again, we have 1d equals negative 2. Okay, we've got one more to try this with. We're going to fill in and set up with 4 and 14. Okay, here's our setup with 4 for x and 14 for y. 4 cubed, 4 times 4 is 16, times 4 is 64a. 4 squared is 16 times b. Then we have 4c, our 1d, and equals 14. So when we go to our technology with our matrices, we're going to need 1, 2, 3, 4 rows and 1, 2, 3, 4, 5 columns. Okay, so we've set up 4 rows, 5 columns. Remember, it's rows by columns here. We'll set our matrix and plug in all of our coefficients. Okay, this is always a good time to double check that you didn't make a mistake. So remember all the time your technology is about to save you from solving this system. So double check with your numbers. Let's see what we get here. I like this. If we're getting nice integers out of a system like this, we probably did okay. All right, it's giving me my A, B, C, and D value. Again, if I click Show Solution, I can see that matrix. We do have all ones in this main diagonal. This time it's a 4 by 4, but all ones and zeros everywhere else. So this is my A, B, C, and D values. Okay, so I've written down my A, B, C, and D values. Let's write our equation. I am going to flip around and put our y back where it's supposed to go, but this would be 1x cubed minus 3x squared plus 0 x's, right? C is 0. So we can skip that term completely and just write minus 2. And of course, how can we tell if this is the correct equation? The polynomial that gave us all those points, we're going to graph it. Okay, here's our graph. X cubed minus 3x squared minus 2. Let's convert this to a table. Now again, it only goes down to 1 and 2, so we can only check 2 of our points currently, but 1, negative 4, 2, negative 6. 3 should give me negative 2, 4 should be 14, whoops, 4 should be 14, 5 is 48, and 6 is 106. Nice. So there are some pretty cool things you can do with this. You could even, if you wanted to, pick 3 points on a graph, so this is just made up and not part of the above problem, but if you picked 3 points on a graph, and you said, I want to know what's the equation of the parabola that went through that graph. There is only one parabola that will go through those 3 points. As long as it's still a function, as long as you don't have 2 points directly above each other, and as long as you don't have all 3 next to each other, right? I can't have an up and down parabola go through those. But you can kind of design your own parabola from 3 points, which is pretty cool. Now we're going to go a step above that. We're going to design our own cubic function, which has kind of this curve. So a cubic function is something where x cubed is the highest degree, like we just solved for. Now, we can use the same thing we just did before, a times x cubed plus bx squared plus cx plus d, and we have these 4 different things we need to solve for. And I might even move my y to the other side over there, right? So we're welcome to do that and find our system of equations. There's nothing wrong with solving it this way. But if we happen to know all of the zeros of my graph, we can use what's called factored form to get our answer a little bit quicker. We haven't really learned that yet, so I might show you at the end of this, but let's just use these 4 points, right? It gave me one specifically here to help me out, but hopefully you found these nice x-intercepts here to help us out. So we've got 4 points, we have 4 unknowns. That should be enough to give me 4 equations. So here are our points. -3, 0. The point up here, which is -2, 1. We have -1, 0. And then we have 3 zeros. There's our 4 points. Let's plug them in and get our 4 equations. All right, here's my 4 kind of blank setups here. Remember, we've got some x and y values to plug in. So we're going to plug in starting -3 for x and 0 for y. We're going to write our new results down here. -3 cubed, you might have to check that with the calculators, -27a. -3 squared, though, makes +9b. -3 times c is -3c, plus 1d equals 0. Okay, so we plugged in that point. Let's plug in -2 for x and +1 for y. -2 cubed is -8a. -2 squared makes +4b. -2 times c is -2c, plus our 1d equals 1. There's our second equation. Next, we're plugging in -1 for x and 0 for y. -1 cubed makes -1a. -1 squared makes +1b. We've got -1c plus 1d equals 0. Okay, last point we're plugging in 3 for x, 0 for y. 3 cubed is +27a. 3 squared is 9b. 3 times c is +3c plus 1d equals 0. Okay, time to go to technology. All right, we're back at that same website. Let's type in all of these coefficients here. Okay, so it's given me my solution here. I can check my matrix. It does have all ones on the diagonal, which means we got an exact solution, all nice zeros everywhere else in that main part. And so here are my values of a, b, c, and d. Looks like we have 1/5, 1/5, -9/5, and -9/5. We got some fractions back. It's kind of an ugly problem. But we now know our 4 values. Okay, so here's our a, b, c, and d values. So we're going to flip our y back around here and write this in our normal form. So a, 1/5 x cubed, plus b, which is 1/5 x squared. We've got c, -9/5 x, and d, -9/5. Okay, well, of course, how do we know if this is correct? Let's graph it and see if it matches. All right, here's my equation. I know some of the graph is obviously off the screen there, but we're more interested in the equation and the table. So let's take a look at our table, and I see, well, remember, we're just checking these 4 points. -3, 0. Okay, well, that's not on my list, but that's okay. We can type it in. -3 does give me back 0. -2 should give me back 1. Nice. -1 gives me back 0. And +3 gives me back 0. And now if I drag this on here, you can see it does look pretty good. Matching our graph above, we can even see those nice zeros. And our point here, which is, I don't know, it's slightly off from what it gave us, but we'll take it. I think it's giving me a local maximum, which is not exactly where our point was. It's not exactly the local maximum, but we obviously saw from our table, -2 is at +1. Again, you are welcome to use this MathPie website. This would be a 4x4 system, and you can just type in the coefficients for all of these, and then W, X, Y, and Z would be your answers for A, B, C, and D. I'm not sure about how they give the answers back. Let's check. Okay, so I went ahead and typed them all in and clicked solve, and yep, it does give you back nice fractions as well, so that was pretty cool. So you're welcome to use this MathCalPie website. I'll link that one as well, and you just need to click on which size system up here.